Welcome to a lesson with Dr. Powell. We're going to talk about modular arithmetic, but in a different setting than in Z. We talk about it in the symmetric group, S4. Now, the operation of composition here is not commutative like it is in Z. But let's review what it means to have modular arithmetic in Z. What if we mod out by 5Z? Now, this is actually a subgroup of Z, and all subgroups of Z behave in a very nice way when we mod out by them. Namely, if I think of bars as being denoting representatives, if I take 21 bar plus 13 bar, this can be done either by just throwing everything under the bar to get 34 bar, which is just 4 more than a multiple of 5. Or I could reduce the representative or change the representative under the bars and then do the same thing. And notice I should always end up in the same place. That is a nice property of modular arithmetic. And we say that a subgroup of S4 that would produce the same type of modular arithmetic idea of reducing or changing representatives and then adding like this underneath a bar in modding and getting the same result would behave normally as it does here in this situation. So we would call it a normal subgroup. There are precisely 4 normal subgroups of S4. Not every single subgroup of a non-commutative group is normal all the time. The 4 are actually itself the identity, which I'll label as a 1. It's a subgroup in its own right. These don't produce anything very interesting in mod arithmetic. There's also all even permutations, but modding out by this just produces mod 2 arithmetic. There's also one more, which is slightly interesting. The Klein 4 subgroup. It has 4 elements in it. Let's look at that group for a minute. It's actually a subgroup of the dihedral group. I'll put a 4 here. 3, so 1, 2, 3, 4. And what it does is it reflects. It interchanges columns or rows, or does rows then columns, which has an effect of interchanging diagonal entries. So it has 4 different things if you include the identity. Interchange columns, interchange rows, or interchange diagonal entries, or just do nothing, which I'll label as a 1. This is K4, which I'm going to call the Klein 4 group, subgroup of S4. So if we mod out by this, we should have the same thing happening as we did up here. Now, how do we show that something is a normal subgroup? Well, in this case, notice that all these elements of K4, at least these top 3, yield all the possibilities of a 2-cycle and then another 2-cycle. You could try this out and explore and look at it. I mean, these are disjoints, so really rewriting these on one side or the other is the same. And you'll notice that these are the only possibilities of having a 2-cycle followed with a 2-cycle in S4. So keeping that in mind, also realize that if I take any group element at all, take its inverse, and I also take the same group element and put it on the left, this one on the right, so this one is done first in composition, and in the middle, I put one of these guys, something will happen. If I put in something like G of 1, look what happens. Goes in here, this undoes what G does, so I have 1 still. I come in here, and I go to where 1 goes, 1 will go to 2. And then it goes into G. So in other words, I output G of 2. So G of 1 will go to G of 2. In a similar manner, if I proceed by plugging in different things, I'll actually notice the cycle type was preserved. Meaning that doing this type of thing, putting an element with its inverse and this over here, actually preserves cycle type, which means that it outputs something that's still in the group K4. I can't get out of the group K4 by doing a G, an element of K4, and G inverse. I always stay in it. How is that useful? Well, that means in particular that I have this idea, which is the same thing as saying that the left coset is equal to the right coset with the same element of G. This right here is the criterion that we need for any G in relation to K4, where G is in the ambient larger group, for a subgroup to be normal. So we actually have a nice working arithmetic. We need this, and K4 happens to be normal. Now let's look at an example of how we can do modular arithmetic over K4. So if we take S4 and we mod out by K4, that means we can reduce representatives using K4 symmetry. Let's have another way of writing permutations in S4. Let's use this as our base representation for the identity. And then let's use something like this to represent 1 goes to 2, 2 goes to 1, 4 goes to itself, 3 goes to itself. So if I rewrite the numbers this way, I actually am talking about a permutation. 1 goes to 2, 2 goes to 1. So the base position of 1 will go to 2, the base position of 2 will go to 1. This is precisely the permutation 1, 2, but written in another way. This is nice because we can easily do reflections right on here and change the representative. So another representative for this might be 1, 3, 2, 4, where I just interchange my columns. Okay, so why don't we try this? Let's take 2, 3, 1, 4, and compose it with 4, 3, 2, 1. Thinking of it as mod in this arithmetic. So one thing I could do is I could change the location of some of my elements here. I could swap these columns. So I'd have 3, 4, 2, 1. And this creates a permutation where 4 is fixed. And then what I could do over here, I could do the same type of thing, maybe interchange rows. So I have 4, 3, and a 2, 1. Now let's take a look at this. Let's do the composition here, thinking of throwing the bar over now, after I've reduced. So I have, and I'm going to think of this permutation in cycle notation. So this is 1 goes to 3. And 3 actually goes back to 1. 2 is fixed, so it's just 1, 3. This one over here is 1 goes to 2. And 2 goes to 1. And 3 is fixed. So I really just have 1, 3 composed with 1, 2. Which ends up being, if I pass 1 in, it goes to 2. Pass 2 and it goes to 1, then it goes to 3. If I pass 3 in, it goes back to 1, wrap around. So I get this guy right here. Now, that was after we changed the representatives. And we got this. Let's see what we get. In fact, I'll write this out before we see what we get over here, let's write this out in the other notation. This is the same as 1 goes to 2, 2 goes to 3, and 3 goes to 1, and 4 is fixed. So that's what we're left with right now. Okay, now let's see what happens over here. All right, let's first rewrite this in cycle notation and with everything under the bar. So this looks like 1 goes to 2, and 2 ends up going to 3, 3 ends up going to 4, and 4 ends up going to 1. Next, I have, well, we have 1 goes to 4. And let's see, 4 ends up going to 2. And 2 ends up going to 3. And 3 ends up going to 1. So wrap around. And we think this is, well, you throw 1 in here. 1 comes in and it goes to, so 1 ends up going to 4, which ends up going back to itself, to 1, because 1, 4, and then 4 goes to 1. So I don't have to worry about a 1. What does 2 do? 2 goes to 3, which ends up going to 4. Okay, so 2 go to 4 in the end. Okay, then 4 comes in, it says it goes to 2, which goes to 3. 3 comes, and now we know 1 was fixed, so it should go back to 2. We can double check. 3 goes to 1, which goes to 2, just like expected. So we get 2, 4, 3. Now, you see this representative here? If I just alter, let's just alter this a little bit by using a permutation, by using one of the representatives of K4, one of the reflections. Let's do diagonal. So if we change things on the diagonal, we would end up getting 4, 3, 1, 2. Let's take a look at what's going on right now with this. Let's think. Well, I know here that 2 will go to 4. So 2 will go to 4. So I'll write that down. And then 4 ends up going to 3. And then, let's see, then 3 ends up going back to 2, wrapping around, and 1 is fixed. Oh, wait a minute. So this representative right here is the same as this right here. It's 2, 4, 3. Look. So really this is the same as this in the mod. Just as expected. And our modular arithmetic was successful. Thanks for watching.